Hello everyone, I'm Ryan Anderson, and I'm going to be showing some of our work on NMR imaging and how that relates to the fundamentals of coupling heat transfer and fluid flow in several experiments. I'm going to first state that everything that is shown here today has been in conjunction with the Magnetic Resonance Microscopy Lab at Montana State University, led by Dr. Joe Seymour. And I'm going to highlight three different systems. A forced convection system, where we have heated fluid enter from the bottom and then move through a porous media system. A natural convection system where we remove that packing material, but we can still just focus on the fluid phase and how its velocity varies in natural convection experiments. And then combining those, we have a natural convection experiment where we put the packing back in there, and then we are measuring the velocity profiles and also analogs to temperature. We can see the temperature of the beads inside this porous media. The key to this, especially if we're doing work that has the porous media, is using two different fluids to do the imaging. The imaging can occur in the longitudinal planes or the transverse planes, shown here, and all the images that you see on the right are in those planes. So let's start with an example of hydrogen imaging of the beads. Why that's important is the beads that we're using here are actually an encapsulated wax that is hydrogen containing. So when that wax melts, going from solid to liquid, more signal can be generated in the NMR, and that's what we see here. So if we focus on the top right, fluid in this case is the forced convection with heated fluid going from the bottom to the top. The red here is at T hot, and you can see that its spatial location changes over time. Everything that's in blue here is at T cold, but you can also see a gradient in the signal. So really this is a qualitative image of the melt front propagation through the bed. But what we're doing right now is around the melt temperature for several degrees C, we can calibrate from the NMR parameters the signal we see here to the actual temperature, so we're getting at quantitative experiments. What's really important though is that there's the coupling between the heat transfer behavior you're seeing here in the top right and the fluid flow behavior that you're seeing in the center in the top images here. So in this case, we switched the imaging technique to use a fluorinated fluid, so doing fluorine imaging, still fluid flow from the bottom to the top in this case. And what we've been able to resolve here are the Z, X, and Y components in the pore space itself. And these velocity profiles that I'm showing here would correspond to experiments that are the same as the heat transfer experiments where I'm showing the melt that's happening in the top right. So we have this non-invasive coupling between the heat transfer and the fluid flow. This led us to some studies on natural convection flow patterns. And in traditional Rayleigh-Benard convection, you would have a system where the height is quite small relative to the diameter. But we have these situations in low aspect ratio containers now where we're doing a narrow diameter and a tall column. And what we note is that we have these strong axial variations in the velocity. So for instance, for one result here at the 10 millimeter mark, we see this, what appears to be more of a bullseye profile. At the 24 millimeter mark, we have something that's more like this C shape here. And at the 34 millimeter mark, we have this four cell emerging. In each of these, the orange and the red color is the positive velocity, and the bluish color there is the down velocity in the negative direction. So depending on the Rayleigh number you have there, that's a function of your temperature that you apply between the top and the bottom and the particular fluid you're using. We get these different pattern variations. We also see something really similar numerically. All of this work has a numerical complement, so this is just one result that's shown here. But symmetrical mesh, setting a hot boundary condition at the bottom and a cold temperature at the top, we are able to see this axial variation in the pattern form numerically as well. Where we're going with this in our future work then is that we are 3D printing these beads into more complex structures. So everything I've shown so far or mentioned in terms of the porous media was using these beads that are on the order of a few millimeters. What we're doing is taking a micro-encapsulated wax where everything is on the order of tens of microns and putting that in the resin and directly 3D printing that into the structure. So here's a hollow cylinder example that's shown here. And from the 23rd minute to about 40 minutes, what you see here is in the two different planes here, both longitudinal and transverse, we see an increase in the signal. That's indicative of that wax in the bead is actually melting. And with the calibration procedure I mentioned, we'd be able to turn something like this into an actual measurement of the temperature in the system. There is some heterogeneity in the beads right now in the examples that are shown here, but we're working that out right now and hope to do more complex structures in the future. Being able to, anything that we can 3D print these in, we can then have fluid moving through these and do much more complex systems. So if you have any questions, feel free to reach out to me. I'm Ryan.Anderson at montana.edu. Thank you.